Symmetry in electric circuits. On the board, you can say some of the circuits which have lot of resistors, and if you see carefully, such resistors have some symmetric properties. They have a definite pattern. Such circuits are said to have some symmetric properties. And in the present lecture, we will see how we can take advantage of such symmetric properties of the elements. Elements means the resistors, the capacitors, or the inductors. So we will see how we can use the properties of symmetric elements in finding the current or the voltage or the effective resistance in the circuit. As I told you, the elements can be the capacitors, the element can be the inductor, the element can be the resistor or the cell. As a model, we are dealing with the resistors, and the same principles of symmetry will be applicable for capacitor, for inductors, for cells, or so on and so forth. So first of all, we will see what is the meaning of symmetry and how we can take advantage of symmetry in certain cases of physical quantities. See, when we talk about symmetry, symmetry means the mirror image, or you can say the identical pattern, right? When we use the word symmetry, it means the mirror image or the identical pattern. Now tell me one thing, suppose we have a pipe which is carrying water, the water is coming in this pipe, okay? And now we have division at this point with two pipes, and both the pipes have same area of cross section. Both pipes have same area of cross section and same properties, okay? All other properties are also same. So see, the division of water at this place will be inclined equally. It will have no preference. It will be inclined equally for both the pipes. The tendency of the rate means the amount of water going per unit time. The tendency of the rate of water going in pipe 2 will be same as the tendency of the rate of water going in pipe 1. So we say here that both the pipes have symmetrical situation. So the rate of flow will be same in both the pipes. Okay. So this is like the illustration of symmetry when some quantity is to be distributed among multiple paths, and the multiple paths are offering symmetric conditions for the flow of the property. Multiple paths are offering symmetric conditions for the flow of the property, then that property get equally distributed in the multiple path. Now let be little bit formal in defining what is the concept of symmetry. So we can say the concept of symmetry is an additional tool. First of all, what is the point to drive home is that taking advantage of symmetry, it is an additional tool. It means if you want to take advantage of the symmetry present in the situation, if you want to take advantage of the symmetry present in the problem, in the situation, so it is not your foundation. This is an additional advantage. It means if you want, you can proceed ahead without using the advantage of symmetry. But of course, it will make your working a little bit lengthy. So symmetry, what is the advantage of symmetry? It gives you some shortcuts in the working method. Okay. So the concept of symmetry is an additional tool which often helps to simplify the distribution of forces, charges, current, and other physical quantities when identical fields of distribution are present. When identical fields of distribution are present. Okay, so what is the pattern of symmetry doing? It is simplifying. It is simplifying the distribution of the physical quantity. It is simplifying the distribution of the physical quantity. Like in this case, if you see in this present case, what was the physical quantity? The rate of flow of water. What was the physical quantity? The rate of flow of water. What is the meaning of identical fields? Here, like there are two pipes, and the two pipes are identical in nature. So both are attracting the same rate of flow of water. Both are attracting the same rate of flow of water. So in circuit, the field will mean branches. In circuits, this is something generalized which can be applicable in all the cases. In the present lecture, we will focus on electric circuits. In that concept, the field will convey the branch, and the quantity will convey the charge or current, depending whether we are dealing with the resistor or the capacitor. So when we have multiple branches or we have multiple fields, multiple paths, and all the multiple paths are offering the identical tendency of attraction of the quantity, the identical temptation or tendency to attract the incoming physical quantity. Like in this case, the incoming physical quantity is the current. and these two are the identical paths, then the quantity get distributed based on the concept of symmetry. So to illustrate, let's see we have an electric circuit and a current I is coming in the main wire, and the current, there is a junction, you can see we have a node or junction at this point, and the current will be divided at this node. So some current will go in the upper branch and some current will go in the lower branch, and you can see both the branches have identical resistance R each. So the division of current in both the branches will have equal tendency, because it is the resistor which decide how much current will flow in that particular branch. So the division of current will have equal tendency. There will be no priority of the current in going one branch over the other because they are identical in nature. So same current will go in both the branches, and by the conservation of current, since total current is I, so when I will be divided equally, in the upper branch it will be I by 2, and in the lower branch it will be I by 2. So both the branches will have the same current. This is some very basic concept of the symmetry. And again, they will meet at this junction and the outgoing current will be I. Okay. So this is how symmetry works. We will see the paths which are dividing the current, and if they have some symmetric pattern, so the current or charges will also get divided in such alignment with the symmetry. More illustrations and more problems will make it more clear. Now, if you see the second illustration, here you can see we have an electric circuit with the terminals A and B. And you can see there is a resistor 3R, 3R, 2R, 2R, and in the middle there is a resistance of R naught. So just think for a couple of seconds, and can you visualize some line or some plane of symmetry in this figure? Is there any line or plane which is dividing the figure in mirror images? So you will say, of course, we can locate. You will say, of course, we can locate a vertical line like this, and this line will act as an axis of symmetry, because this line is dividing your circuit in two mirror images. If you see, right and left sides are the mirror images of each other. So there is a line of symmetry present in the circuit. Solely consider there is a line of symmetry present in the circuit. And if a line of symmetry is present, which is dividing the circuit in two right side and left side mirror images, so other properties of the circuits like the voltage, means the potential difference, as well as the current will also be divided symmetrically. Now it means the amount of current flowing in the upper branch, say this branch has a current I1. So on the right hand side also the current will be I1 by the basis of symmetry. See here, one thing is there, strictly we cannot say current flow is symmetric, because had it been symmetric, the flow would have been like this, the mirror image, like this, about the line of symmetry. Had it been precisely symmetric in technical sense, so the current flow would have been like this, but the current is in the same direction. So current direction is not the mirror image. The magnitude of current is same. Okay, so the current will have the same magnitude on both the sides of the axis of symmetry. And when it has a current I1, it is also having a current I1. It means at this point, so this is a node A, there is no division of current, because complete I1 coming at A is going away from A. If you apply the concept of symmetry in the lower branch and say this branch has a current I2, so by symmetry, this branch will also have a current I2 in the same direction. And again, on the same logic, you can say, if it is a junction B, so B is having no division of current. And since no current is dividing at A and no current is dividing at B, so on the argument of symmetry, what you can judge? You can judge that R naught will have no flow of current, correct? Because no current is getting divided at A, no current is dividing at B, whole I1 is coming and whole I1 is leaving at A, and same thing goes for I2. So R naught will be a passive element in this circuit. There is no current in R naught. So many things can be concluded by the concept of symmetry, okay? Now we will see when we analyze the circuit. So there are two different ways for analysis of the circuit. One is the nodal analysis using Kirchhoff's laws, which is a generalized rule. Okay, this is a generalized rule which can be applicable even if there is symmetry or even if there is no symmetry. As I told you, symmetry is an added advantage. You can also do the problem without taking advantage of the symmetry. But what is the advantage of symmetry? It makes your working less lengthy and gives you some advantage in reducing the number of equations and working. So nodal analysis of Kirchhoff's laws is a generalized rule which we have seen, and there is a separate lecture on nodal analysis. In the present lecture, we will focus on the second approach of circuit analysis, the properties of symmetry, which is a special case. This is not a generalized case. It is applicable. You cannot solve all the circuits by symmetry properties. The necessary condition for the analysis of circuit using the properties of symmetry is that symmetry must be present in the circuit. Symmetry must be present in the circuit. So it is a special case which is the subject of the present. Now let's see the circuit analysis using symmetric properties. So if the circuit contains certain symmetric properties of elements like resistors, capacitors, inductors, etc., we can take advantage of the same and analyze the circuit using such symmetric properties. Okay, if the circuit has, you can see there are some circuits which are having certain symmetric properties, and we will explore more in the lecture how we can identify such symmetric properties by just look at a circuit. So if the circuit contains certain symmetric properties of elements like resistors, capacitors, inductors, we can take advantage of the same and analyze such circuit using such symmetric properties. Now let's see how many types of symmetry we will study. So basically, we are going to analyze the circuit using four kinds of symmetry. The first one will be the mirror symmetry, which is also called the perpendicular axis of symmetry. This will be the subject of present lecture. The second one is the folding symmetry or the parallel axis of symmetry. The third one will be the shifted symmetry, and the fourth one will be the path symmetry. So in all, we will see how we can analyze the electric circuits by four types of symmetry. You can note down all the types of symmetry, and this will be in the present lecture. That is your lecture 1 or part 1, and this will be in the subsequent lecture, lecture 2, lecture 3, so on. Okay, so first note all the four types, and then we will explore on the first type, that is the mirror symmetry or the perpendicular axis of symmetry. So let's see, when you can say, how can you look the circuit and say the circuit has a mirror symmetry or perpendicular axis of symmetry? See, first of all, you will see the direction of current. You will make a line, you will make a main line which is denoting the direction of current. So suppose, see this figure, and so the current is coming like this. The cell is connected across A and B. The cell is connected across A and B. So we can say this is the direction of current. Okay, this is your direction of current. Now, if the circuit is having mirror images about an axis perpendicular to the direction of current, I repeat, if the circuit is having mirror images about an axis perpendicular to the direction of current, then we say the circuit has a mirror symmetry or perpendicular axis of symmetry. So there must be some symmetry present. You must locate some axis of symmetry perpendicular to this pink colored line. You must be able to locate an axis of symmetry perpendicular to this pink colored line, then only the circuit can be said to have a mirror symmetry. So you can see, if we make a vertical line like this, then this vertical line can be set to be an axis of symmetry because it is dividing your circuit in two mirror images, 3R, 3R, 2R, 2R. And since this axis of symmetry is perpendicular to the direction of current, so we say this is mirror symmetry, or you can say mirror axis of symmetry or perpendicular axis of symmetry. So this is how you identify whether the circuit has a mirror symmetry or not. It is not necessary that every circuit will have a mirror symmetry. So first of all, for applying the properties of the mirror symmetry, which we are going to explore shortly, the very first place you have to check whether the circuit has a mirror symmetry or not. So see this illustration. Suppose a cell is connected between A and B, and this is the main current I, and this is the current I leaving. So if I'm making the direction of the current, so this will be the main direction of current. And if you see, there is a line which is acting as the axis of symmetry, this yellow dotted line. This is, again, I can say a mirror axis, because this axis is dividing the circuit in two equal halves, two mirror images on right hand side and left hand side, and moreover the axis is perpendicular to the direction of current. So you can see such circuits have mirror axis of symmetry or perpendicular axis of symmetry. Now let's see what are the properties. First of all, you will note down this thing, what is the meaning of. You can still the video whenever you want to write something, you can pause or still the video. Okay, first of all, you will note down what is the meaning of mirror symmetry or perpendicular axis of symmetry, and you make two illustrations. You can make the illustrative figure. This is figure A and this is figure B. Okay, now the main point. Now we'll see what are the properties in the mirror axis of symmetry. If the circuit is having perpendicular axis of symmetry or mirror axis of symmetry, then what are the properties which can be employed, which can be applied? So write mirror symmetry properties. In the notes, you can write mirror symmetry properties. Property number one, points on the mirror axis have the same potential. Points on the mirror axis have the same potential. Okay, this is very important property. So if you see in this circuit right now, we have seen in illustration 1, this is the mirror axis symmetry, right? And all the points lying on this axis of symmetry will have the same potential. So say this is node, say point 1, and this is node, say point 2. So surely you can say V1 will be equal to V2. Okay, all the points on the mirror axis will have the same potential. So in this case, if you see, already we have seen in illustration 2, if you're making a mirror axis, it will be something like this. Okay, and of course this is cutting the middle of the resistor 2R. This is cutting the middle point of the resistor 2R. So if this point is A, this point is B, and this point is C, so surely you can say VA, all the 3 points are lying on the mirror axis of symmetry, will be equal to VB, will be equal to VC. That is the first property. Okay, that is the first property. And what can be concluded by this property? What can be concluded by this property? So we know basics of electricity. For the flow of current, there must be a potential difference. There must be some voltage. If the 2 points are equipotential, if the 2 points are at same potential, no current will flow between them. No current will flow between them. So we can say there will be no current through R0. In this branch, there will be no current. Okay, because they are at the same potential. So you can conclude no current in R0. Okay. Now in this case, remember one property, since point A, if you want to locate point A, so say if you have a resistor like this, say 2R, and you have to divide it. So you can make it like this, 2 in series, R and R, with a point A in between. So this will be the skill we will employ in the applications when you want to divide some resistor, getting its midpoint as a clear separate point. So if it is 2R, it can be divided into 2 series of RR. If it is R, it can be divided into 2 components in series, R by 2 each. Okay, so write the first property. You can write the first property. Points on the mirror axis have the same potential. Make these two figures and mark V1 is equal to V2 in this figure. VA is equal to VB is equal to VC. So they are equipotential points. And then this is skill, how we will divide the resistor. Now see the second property of the mirror symmetry. Branches which are mirror images about the mirror axis have the same current. That is, the branches which are the mirror images, like in this case the right hand side and the left hand side, have the same current. They have the same current. Okay, this already we have seen in the illustrations. So in this case, we can see this is the mirror symmetry. And if you see these branches, so if the current is 3R is I1, so this current will also be I1, and these are also symmetric elements. If the current here is I2, this branch will also have a current I2. So we can conclude that there is no division of current at junction A and B, because already I told you in the illustration, the complete current coming at A is going away from A, and same thing is going for node or junction B. If you see this circuit, suppose the main current is coming at A is I, and the outgoing current will also be I, and there is the perpendicular axis of symmetry we can see like this. So surely you can say the current on both sides of the circuit will be same. So if this branch has a current I1, this branch, that is the symmetric corresponding symmetric element of this branch, will also have a current I1, correct? If this branch have a current I2, this is R, R, R. So this is the symmetric element of this element. So it will also have a current I2. Now if you see, suppose this node is O, so when I2 comes to O through this branch, when I2 is coming to O through this branch, whole I2 is leaving from O through this upper branch. That is, no portion of I2 is getting divided at O. Mind it, no portion of I2 is getting divided at O. No current division at O. And say it has a current I3. Now if you see this branch, middle branch, it is also symmetric on both the sides. So if it has a current, say I4, this will also have a current I4. Okay. And if you see the lower branch, 3R, 3R. So this is also symmetric. This is R, this is R, this is also symmetric. So again, you can apply the rules of symmetry. Suppose this is a current I5. So this will also have a current I5. And if this branch has a current I6, this will also have a current I6. Again, you can see the complete I6 coming through this branch at O is getting returned in the lower branch through O. So there is no mingle of current at O. Though there are three wires intersecting, there are so many, first wire in the upper segment, second wire in the lower segment, and the middle wire. So there O is a node, but there is no intermixing or division of the current from the upper segment, the lower segment, and the middle branch at O. And if this current you can take as what? I7. Okay. So this is how we can label the currents on right hand side and left hand side on the basis of the axis of symmetry, mirror axis of symmetry. Okay, you can note it down. The third property, and third property will have three applications. So third property will deal with the points or nodes on the mirror axis. To see the first application of the property, all the nodes or junctions on the mirror axis can be separated out, eliminating the resistor between those points. Okay, so if there are certain points on the mirror axis, of course we have seen they will have same potential. They will have same potential. So when they will have same potential, we have seen in this circuit, this is the mirror axis. And if this is the mirror axis, then we have seen this point A and this point B are at same potential, correct? This already we have seen. So if they have the same potential, so this resistor which is between these 2 points is ineffective. It is a passive element of the circuit. It has no role. There will be no current through this element. So what you can do, you can make an equivalent figure like this. You can eliminate this element and you can make an equivalent circuit figure, something like this. A, B, and this is your 3R, this is your 3R, this is your 2R, and this is your 2R, and this is point A, and this is your point B. There is no role of R naught, you have eliminated R naught. So that is first property for the nodal points on the mirror axis. Okay, if there is some element between such nodal points, you can remove that element. Okay, note it down. Now, the second application of the third property, if there are different points on the mirror axis, you can apply one or more of such properties. It is not necessary that you are applying all the properties in the same circuit. It depends on your convenience. We will see the application right now. If there are different nodes or junctions on the mirror axis, so since they have the same potential, this we have explored. Like in this case, we have seen so many times, this is the mirror axis, and this is point A, and this is point B. So already we have seen VA is equal to VB. Points on the mirror axis, they are having the same potential. They are equipotential points. So you can make an equivalent figure. You can make an equivalent figure treating them as a single point. Treating them as a single point. You can write A comma B, and this is your capital A, and this is your capital B. So you will have a figure like this. Correct? There is no role of middle register. So this is your 3R, this is your 3R, this is your 2R, and this is your 2R, and this is A, and this is B. So this is the second application of the third property. If there are different points on the mirror axis, since they are equipotential, so they can be treated as a single point in the circuit. They can treat it as a single point in the circuit, and the middle register or middle element will appear away. It will go away. There will be no role of that element. So either you can go by for this approach, the approach A, that you are not treating them as a single point, but simply removing the middle element. Are you getting the point? Either you can go for this equivalent circuit, you are not treating them as a single point, but simply removing the middle element. Or you can go for this approach. You are treating them as a single point, and again the middle element will be eliminated. Now, third property which have application, third application of the third property. See, when we have a perpendicular axis of symmetry, like in this case, if you see right hand side and left hand side, so this is the current axis, this is the direction of current, correct? This is your direction of current, and this yellow axis is the mirror axis, because it is dividing your circuit in two mirror images perpendicular to the direction of currents. So all the properties of mirror axis will hold. So if you see these two are symmetric element, so if it has a current of I1, this will also have a current of I1, correct? If this element has a current of I2, this element will also have a current of I2. So if this is a point O, and you can see this upper branch is bringing a current I2, then whole I2 is going in this upper branch. There is no division of I2 at O. The point is that no division of current at point O, correct? So if there is no division of current at point O, what can you do? And of course, if this has a current I3, again you can make this as I3. Now when there is no division of current at any point on the mirror axis, then that point can be opened. You can make an equivalent circuit separating out that point. Separating out that point, you can make it disconnected. Actually, it is not disconnected. They are connected. Okay. and there would have been some division of current has the condition been not symmetric. But on the basis of symmetry, you can say whole current coming is going in the upper branch and whole current coming in this left branch is going in the right branch. So basically, whether O is joined or is not joined doesn't matter. So in such situation, what we can do, we can make an equivalent circuit, something like this. And see, I'm opening the circuit at O. Can you see? This is R, 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 and this is R, this is R, this is R, and this is point A, and this is point B. Now see, what I've done, I've made a gap here, and this gap is reflecting that in effect, as far as the distribution of current is concerned, you can treat this node and this node as separate nodes. I can open the circuit. So this is the third property. When the current is not divided at any node, you can open the circuit at that node. Okay. So these are the three properties which now we are going to apply in the problems of symmetric circuits, perpendicular axis of symmetry. Now let's see the first illustration. And I will do the problem with multiple approaches. It depends on you which approach you find suitable for you. And some circuits will have more than one symmetry. Right now we have seen there are four types of symmetry: perpendicular or mirror axis, parallel axis, folding symmetry, shifted symmetry, path symmetry. Right now we are doing the problems on the basis of perpendicular or mirror axis. In the next lecture, we will see the properties of folding symmetry or parallel axis of symmetry. Then we will see some circuits will have both the symmetries. Some circuits you will find which will have the perpendicular axis of symmetry as well as the parallel axis of symmetry. So properties of both such symmetries will be applicable in such circuits. Right now we are just focusing on mirror symmetry, okay? Now in the given circuit, find the resistance between the points A and B. When we say between the points A and B, you know the basic. It means if you are bringing a cell, then the cell will be connected between A and B. We need not to connect the cell. That is something we will think whenever you're finding the resistance between 2 points. It means the voltage will be applied between those two target points. So basically, this will be the current axis. If you are finding the resistance between A and B, so this will be the current axis. Now, can you see, is there any line of symmetry? So if you see, this is R, which are the mirror images, 2R mirror images, 3R mirror images. So we have a vertical line, and this vertical line is acting as an axis of symmetry. And since this vertical line is perpendicular to the axis of current, so we can say it is a mirror symmetry. So all the properties of mirror symmetry will hold. So say I'm putting these points, nodes say A, B, C. Now I have to find the equivalent resistance between capital A and capital B. So we have seen right now so many properties. We have seen three properties. And in the third property, we have seen three applications. So we will apply all these points here. So one of the property was when we have the perpendicular axis of symmetry, all the points on that perpendicular axis of symmetry will be at same potential, and we can eliminate the middle elements. So I'm applying that approach, say approach 1. Eliminating the middle elements. Okay, if I'm eliminating the middle elements, so your VA will be equal to VB, and this will be equal to VC. So I can make a new figure. 5R and 3R will be eliminated. So you will have circuit something like this. Correct. This is your point A, this is your point B, and this is your point C, and this is your B, and this is your A. And you can see the resistor. R, 2R, 2R, 3R, 3R. This is R, this is R, this is 2R, this is 2R, this is 3R, this is 3R. Okay, this is the first approach. Elimination of the middle elements. Now this is in series, this is in series, this is in series. We have to find between A and B. So I will have three effective resistances between A and B in parallel combination. This is your 2R, this is your 4R, and this is your 6R. Now it's very straightforward, no? Very basic thing. Now this is the parallel combination. So the equivalent will come to be 1 by R will be R dash, I shall let us say 1 by 2R plus 1 by 4R plus 1 by 6R, correct? So I'll have the LCM as 12R. So I'll get how much? 6 plus 3 plus 2, 6, 11. We'll get 11 by 12R. So R dash will come to be 12R by 11. That is your answer, correct? This is your answer to this problem, 12R by 11. Got it? So this you have done by first approach. What you did, you have taken the points on the mirror axis and you have eliminated the resistors between such equipotential points, and you have denoted those points at separate points. So you got three effective resistances in parallel, 2R, 4R, 6R, and then you simply have applied the formula for the parallel combination, 1 by 2R, 1 by 4R, and 1 by 6R, correct? Now let's see second approach. One property we have seen, we can eliminate the middle resistors. One property we have seen, we can denote all the equipotential point, we can denote all the equipotential points as a single point. And of course, when you will be denoting as a single point, there will be no role of the middle resistor. Both approaches are equivalent. It depends on you how you are making the equivalent circuit. Approach 2. Now I am denoting the points of same potential as equipotential points. Okay, and I'm denoting the points of same potential as equipotential points. So I got A, B, C. So I will make a new equivalent circuit. This is a point A. This I'm making point A, comma B, comma C, and this is the final point B. Now, if you see, when you join A, B, and C in this circuit, when you will join A, B, and C, short circuit, it means short circuiting the points A, B, and C. Joining means short circuiting the points A, B, and C. Already we have seen in the basics of electricity. So 5R and 3R will be eliminated. They will have no role. So this R, 2R, and 3R will be connected in parallel, and same thing will go for the right hand side of the circuit, R, 2R, and 3R, correct? So I will have something like this. R, 2R, 3R, and same thing will be on R, 2R, 3R, correct? Now I can make the equivalent figure. This is point B, this is A, B, and C, and this is point A, and these three are connected in parallel. So if R dash is the equivalent, I'll get 1 by R plus 1 by 2R plus 1 by 3R. So I'll get 1 by R dash as the LCM will be 6R. So we'll get 6 plus 3 plus 2. So 1 by R dash will come to be 11 by 6R. So R dash will come to be, sorry, this R will be in denominator. So R dash will come to be 6R by 11, correct? And same thing will be for the right hand side, both are identical. So it will be 6R by 11, 6R by 11. Now these two are connected in series combination. So between A and B, you will get 6R by 11 into 2. So 12R by 11 is your answer. Now see, you are getting the same answer, and of course the answer must be the same, because simply applying the different approach won't affect your answer. So your answer is how much? By approach 1, you are getting the same answer, 12R by 11, and by approach 2, treating them as the same point, you are getting the answer 12R by 11. Got it? So this is how we did illustration. 1. Okay, now let's see the second illustration. In the given circuit, we have to find the equivalent resistance between A and B. So A and B are the target points, and the line joining the target point will constitute the current axis. So this will be your direction of current, main direction of current, that is the current axis. Okay, this is a point B. And can you see any axis of symmetry perpendicular to the current axis? So of course you can see this is your axis of symmetry, which is dividing the circuit into mirror images. So this is, since this is perpendicular to current axis, so this is the mirror axis of symmetry. So all the properties of mirror axis will hold. So if I label the points, say this is point A, this is point B, and this is point C. So the potential of A, B, and C will be same. We will have same potential. VA will be equal to VB is equal to VC. Now again, you can solve the circuit by both the approaches. What you can do, you can short circuit these points. That is approach 1. We can treat them as equipotential point. That is, simply we are short circuiting this point. So when you treat them as same point, the middle register will have no role. So I can make some equivalent figure like this. This is your target point A, and there is a register R. Then we have the point C, comma B, comma A, and then we have the target point B, and there is a register R. We have taken account of these two R. This will have no role. Now see, there is a register R between A and C. So we have between A and C R, and between C and B there is R. So we have between C and B R. Okay, we have taken account of these two registers. Then there is R between A, small a, and capital B. So we have this R. Wait 1 second. And we have one R between which point? B, small b and capital B, and small a and capital B, small a and capital B, small b and capital B. Then we have capital A and small a. So this is capital A and this is a small a. So we have this R. So this is your equivalent circuit. Okay, now these three are in parallel. We can say these three are in parallel, and so are these three are. So I will have again reduction. I will have one more reduction. This is point A, and this will be R by 3, and this is R by 3, and these two are in series combination. So between A and B, the answer will be 2R by 3. This will be your answer, okay, for this circuit. That is first approach, short circuiting the equipotential points. So the second approach is you can eliminate the middle register between the equivalent point, as we did in what I suggest you don't copy approach 2, work it out yourself and you will get the same answer. Already we have seen in illustration 1, to work it out yourself. So we can eliminate the points and we will have, this is point A and B, and from A, since this will be eliminated and this will be eliminated, the middle register between the same potential point. So I will have RR, then RR, and then again So again, if I'm reducing it, I will have 3 parallel 2R, 2R, 2R between A and B. So the answer will come to be A and B, and you'll get 2R by 3. See, you're getting the same answer, 2R by 3. So you can go by either way. So once you get practice of some circuits, so as I told you in the earlier segment of the lecture at the very beginning, such circuits seem to be or appear to be tough or complicated, but solving them is very straightforward step. That doesn't require much depth. It's simply based on the symmetrical configuration. Many of the circuit you can solve even without picking up the pen. So see the third illustration. Find the equivalent resistance between the points A and B. Find the equivalent resistance between the points A and B. That means the cell will be connected between the points A and B. So your current axis will lie between A and B. So this will be your current axis, and right now we have to check whether we have the perpendicular or mirror axis of symmetry or not. There are basically 4 types of symmetry. Maybe other symmetries will also be present, but right now in this lecture we are focusing on the perpendicular axis of symmetry. So you can see there is a vertical line which is acting as the mirror axis of symmetry. So all the properties of mirror axis will hold. So if this is point A, this is point B, and this is point C. So by the mirror axis of symmetry, we can say the current in this R, if it is I1, this will be I1. If this current is I2, this will be I2 by symmetric property, and this is I3, this will be I3. In this circuit, there will also be the properties of parallel axis of symmetry, but right now I'm not going for those properties since we have not studied right now the parallel axis of symmetry. That we will study in lecture 2. So we can see we can also solve this circuit by parallel axis of symmetry. Right now we are limited to perpendicular or mirror axis of symmetry. So there is no division of current at the point B. No division of current at node or junction P. Correct? So what we can do, we have seen when there is no division of current at any node, we can open the connections at that node. In the equivalent circuit, we can open the connections at that node. So I'm doing it by approach 1. Approach 1, opening node B. I will be making an equivalent figure and I will open node B. So I will have this as the target point A, and this is B, this is R, and this is R, and this is R 3 times. So I'll get R, and then there are 2 R. This is R, and this is R, and this is a point B, and this is a point B, and the symmetric thing is below the current axis. R, and this is a point B, correct? So this is your equivalent circuit by this approach. Okay, now if you see, if I label this point as, say, that is ABC, say D, E, F, G. So between D and E, these two are in series, and so are these two bottom resistors. So I can go one step further reduction. So I'll have A, R, this is point B, and I'll get this is your point D, this is R, and this will be 2R, and this is R, and this is R. An identical thing will be for the bottom portion. this is R, this is R, and this is 2R, and this is R, and this is point F and G, and this is O, D, and E. Now, of course, you can say these two are in the parallel combination. So they will have the, say, resistance has an equivalent. Give it some name, say R dash. See, it will also have R dash being identical. So R dash will be the parallel formula R1 R2. So 2R multiplied by R1 plus R2, that is 3R. So you'll get how much? 2R by 3. So your new figure will be, this is A, and between A and B, these two are in the series combination. So I can make as 2R, and then I will have this is how much? 2R by 3, R, and identical things for the bottom portion, 2R by 3, R. Now I can again go one step further reduction. Now these three between A and B are in series, and identical is the case for the bottom portion. So I'll get equivalent as R plus 2R by 3 plus R, that is 2R plus 2R by 3, that is 6, 8R by 3. So I'll have between A and B, I have three registers, 8R by 3, 2R, 8R by 3 in parallel combination. So now I can get a single register between A and B. I can apply the equivalent formula. 1 by R dash is 3 by 8R plus 1 by 2R plus 3 by 8R. So I'll get 1 by R dash as the LCM will be 8R. So I'll get 3 plus 4 plus 3, 6, 10 by 8R, that is 5 by 4R. So R dash will come to be 4R by 5. So your answer will be 4R by 5. That is your answer to the problem. So this is how we applied the properties of perpendicular axis. This is how we have applied the property of perpendicular axis or mirror axis, and we have opened the node at B. We have opened the node at B, correct? So suppose if you want to solve this very problem with another approach, you don't want to open the node at B, and you want to treat the point ABC as a single point since they're equipotential. So they can be short circuited, correct? So if I'm going for another approach, that is equipotential points. That is, I'm short circuiting the circuit. So in this case, one of the fundamental we will use, which I've told you in the beginning, if this is a resistor R and this is a middle point A, so this can be denoted, you can break it in two equivalent half, both half of this value. So R will have a half value R by 2 with point A in the middle. Okay, this is a skill we have seen in the beginning of the lecture. So here you can see you want to denote point A, B, and C as a single point. You want to denote point A, B, and C as a single point. So let me make first I'm decomposing R. Okay, 1, 2, 3, and then we have two registers like this. So this will be R by 2, this will be R by 2, this is your point A, this is your point B, this is R, this is R, this is R, 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 this is A, this is B, and this we have denoted D and E. And symmetric is the case for the bottom portion, correct? R by 2, R by 2, R, R. And this is point here, F, G, and this is your axis of symmetry, and this is a point C, correct? So see what I did in the first step, I have broken this R in two equal registers in series, each of half the value of the register to be broken, R by 2 each. Now what I'm going to do, I will make an equivalent circuit treating the points of same potential as a single point, or short circuiting, that is A, B and C. Now I will join A and B, and this is the point D. So this is I'm denoting as D, and here I'm denoting as E, and I will take account of each register and putting the mark that that resistance has been taken into account to avoid any confusion. So between A and B, we have a resistor R, and between B and capital B, we have again a resistor R. So these two have taken care of. Then we have R between A and D. So between A and D, I'm making R, and between D and A, we have R by 2, R by 2, and between D and B, we have R, correct? Between A and E, we have R by 2. Between E and B, we have R, and between B and E, we have R. Okay, this is the upper configuration. And here you can make point C, this is point F, and this is point G. And in the bottom configuration, the things are very identical. So between A and F, we have a resistance R. Between F and B, we have a resistance R. Between F and C, we have a resistance R by 2. Between C and G, we have a resistance R by 2. Between B and G, we have a resistance R. And between G and B, we have a resistance capital R. So this is the first reduction method. Okay, and the target points are A and B. We have to find the resistance between A and B. Now if you see these two, between D and A, these two are connected in parallel, these two are connected in parallel, these two are connected in parallel, and these two are connected in parallel. So I'm going for one step of further reduction. So R and R by 2 say has equivalent R dash, so it will be R1 into R2, R plus R1 plus R2. So R plus R by 2 is, so I'll get R square by 2, 3R by 2. So I'll get as R by 3. So all these yellow dotted registers have a value of R by 3. So I can make a new figure. This is point A, this is B, this is R, this is R. Okay. Now this is a point D, and this is a point E. This is R, and this is how much? R by 3. This is R by 3, and this is how much? R, and symmetric will be the case for the bottom portion. This is how much? R. This is R by 3, and this is R by 3, and this is R, correct? Now I'm going for further reduction. So these two elements, if you see between point A and B, these two elements are connected in series, and so are these two elements, and same thing go for these pairs, right? So r plus r by 3 is 4r by 3. So you will have this is B and this is A, and this is 4r by 3, 4r by 3, r, and same thing will be applicable for the bottom portion, 4r by 3, 4r by 3, correct? Now go for another reduction. Now this combination you can say is connected in parallel, and so is this combination. Both will have the same value of the equivalent. So let us find the equivalent as r dash of the 3 parallel. So 1 by r dash will be 1 by 4r into 3 plus 1 by r plus 1 by 4r into 3. So 1 by r dash will come to be 4r is the LCM, 1 plus 4 plus, sorry, that is 3, 3 plus 4 plus 3. So we'll get 4, 3, 3, 6, 10 by 4r. So r dash will come to be 4r by 10, that is 2r by 5, correct? Now you have between A and B 2r by 5 and 2r by 5 which are connected in series. So straightforward you can say now between A and B the equivalent is 2 times of this, that is 4r by 5 is your answer, right? So even by the short circuiting the circuit you are getting the same answer 4r by 5, and by approach 1 which you did you got the same answer 4r by 5. So it is independent how you are making the equivalent circuit. We have seen the same problem by two approaches, one by opening the connection at B and one by short circuiting the circuit for the points A, B and C, correct? Okay, I hope I've gone through it. If you have any problem you can always contact me. Now let's see the fourth illustration. That was the third illustration. Now we are going for the fourth illustration. In the given circuit, find the resistance between the points X and Y. So X and Y is the target line, that is the main current line is X and Y. This is the current axis. And you can see there is the perpendicular axis of symmetry. There is an axis present which is dividing the circuit in two equal mirror images on the right hand side and left hand side. So this is a, since it is perpendicular to the current axis, so this is a mirror axis of symmetry. And now we can label the point, say this is a point A and this is a point B and this is a point C. So point A, B and C will have the same potential, correct? Now you can solve the problem. Of course, the current, whatever the current will be in this I1, same current will go through this element I1. Whatever the current will be here I2, the same current will go through I2. There will be no current in the middle resistor R. We have seen so many times. So you can remove this middle resistor that I'm doing by approach 1, removing middle resistor. So I will have something like this. This is your target point X and this is your R. Now I will have, this is a point B and this is R and this is R, and then I will have this is R and this is R, and this is a point A, and the target point is X and Y. So between X and Y you can clearly see this is the series combination, this is the series combination. So I can make an equivalent figure something like this. This will be R and RR will be 2R, and again RR will be 2R. Now this will be in, you can say, the parallel combination. So 1 by r dash will be 1 by 2r plus 1 by 2r plus 1 by r. So 1 by r dash will come to be 1 by r plus 1 by r, that is 2 by r. So r dash come to be what? R by 2. So your answer will be between A and B, your answer, the equivalent will be r by 2. That is the answer. This is how you removed. This is how you removed the middle register. There's one more approach by which you can do. You can treat A and B as a single point. That is short circuiting. I guess don't see for approach 2. You can work out yourself and check out. You must get the same answer. So I'm short circuiting the circuit. So A and B can be treated as a single point. So we have one resistor between the target point A and B, capital A and capital B, and small a and B I'm treating as a single resistor. This is R, this is R, this is R, and this is R, correct? And middle one have no role since A and B are short circuited. So these two are in, of course, you can see in parallel combination, and so is this pair. So you'll have A, B, and this is A comma B, and this is what? R by 2, R by 2, and this is R. Now they are in the series combination. So again, you can make this is A and this is B. R by 2 will be R, and this is R. Now this is the parallel combination between A and B. So your answer will come to be R by 2. You are getting the same answer, correct? Okay. So you must now you must have become very comfortable with solving such circuits, and you can do. There are multiple approaches for solving the problem. Now, say in the given circuit, find the resistance between the points A and B. Fifth illustration. So this is not A and A. There is some typographical. It's written X and Y. The instruction of the problem says A and B. So let's, according to the instruction, let us write the target point as A and B. Okay. So we have to find the resistance between A and B. So this will be your current line, the current axis. And can you locate the perpendicular axis of symmetry? Of course, we can locate. This vertical line is dividing the circuit in two mirror images. So this vertical line is the mirror axis of symmetry. And if I label the points on the mirror axis A and B, so they will be at the same potential. They will be at the same potential. And if there is a current, say I1 in this branch, then this branch by symmetry will have a current I1. Already we have seen such properties many times. And if this has a current I2, so this branch will also have a current I2. So there is no division of current. There is no division of current at the node B. Right? So we can again solve the problem by multiple approaches. Opening node B, small b node, we are getting it opened. That is approach 1. So I will have the equivalent circuit. This is capital B, this is small b, this is A, this is 2R, this is 2R, and this is your 2R, this is your 2R, this is your 2R, this is your 2R. Okay, and then this is 2R, this is 2R, and this is your A, and this is your B, correct? And so this is C, and this is D. Now you can straightforward, you can solve it, correct? Suppose this is between C and D, these will be in series giving you a 4R, and this will be in again series giving you 4R, and 4R 4R. I'm doing for a straightforward calculation. 4R 4R will be in, and this will be in series giving you 4R. This is A and this is B. This is C 2R. This is a D 2R, and this is how much? 4R, and this is how much? 4R, and they are in the parallel combination. So we'll get A, B, 4R, and this is what? 2R, 2R, 2R. And now these three will be in series combination. So you'll get A, B, 4R, and this will be 6R. Now these two are in straightforward parallel combination. So 4R into 6R divided by 10R. So R will get cancelled away. 5 by 3. So answer will be 12R by 5. That is your answer of the equivalent resistance between A and B. This is the point B. Okay, can you do it by another approach too? Can we short circuit A and B? Yes, of course you can short circuit A and B. You can treat them as a single point. So I advise you also work out this problem by approach 2, short circuiting the points A and B, and then find the equivalent resistance and check out. You must be getting the same answer. You must be getting the same answer, 12R by 5. Got it? So this we have seen. What is the concept of symmetry? What is the concept? There are 4 types of symmetry: mirror symmetry, folding symmetry, shifted symmetry, path symmetry. In today's lecture, we have covered exclusively the mirror symmetry, the perpendicular axis of symmetry, and we have seen the properties applicable for such mirror symmetries and how we can find the effective resistance using such properties. In many problems, there are multiple approaches. Now, in the second lecture, in the next lecture, part 2 of symmetric circuits, we will start with the parallel axis of symmetry or the folding symmetry. And then we will see, after these two symmetries, there are many circuits in which both the symmetries will be present: the perpendicular axis of symmetry as well as the parallel axis of symmetry. So the properties of both such symmetries will be applicable in such circuits. So in the second lecture, we will meet with the parallel axis of symmetry. In the meantime, work out